Hello, my name is Joshua Williams, and this is my Physics 2211 Lab 1 of constant velocity. Now, to introduce everything, the purpose of this lab is to analyze an object's motion at a constant speed without changing direction, and to compare the analysis to a computational model based on Newton's second law of motion. The assumptions made in this computational model are that external forces are negligible, meaning that no friction or air resistance is accounted for. It also says that one-dimensional motion is the only motion present, meaning that there's no displacement in the y direction. It also assumes that normal force will equal gravitational force, meaning that the force exerted on the object by the surface is equal to gravity. Now, the physics fundamental used in this is Newton's second law, that states that net external force on a system is equal to the system's change in momentum divided by the change in time. So as you can see in the equation here, F net equals delta momentum over delta t. And this can be derived into the velocity update formula, which states that final velocity equals initial velocity plus acceleration, or F net over m, times change in time. Now, the results of the experiment show that the computational model accurately portrayed the real-world displacement versus time graph. However, the real-world graph of velocity versus time is not identical to the ideal representation given by the coded model. The procedure of this experiment was to record a video of a marker rolling at a constant velocity in a straight line, import that video into a program called Tracker to analyze the object's change in position frame by frame, and then finally create a computational model in GlowScript of the object's predicted motion using fundamental physics properties. Now the tracker analysis shows that marker by frame across the table, and you can see from these graphs right here, position and velocity, that we were able to collect all the data throughout the time that the marker was rolling across the table. From the video, we saw that the total time it took for the marker to roll across the frame was 1.35 seconds. The initial position was 0.01 meters in the x direction, and the initial velocity was 0.74 meters per second in the x direction. For our computational model, we entered the ball position and ball velocity as vectors, and we set F net equal to 0 because, again, we assume that there are no friction or air resistance accounted for in our model. And for the velocity update formula, I set ball velocity equal to ball velocity because they would be the same if there's no net force externally put onto the system. And as for the position update equation, we set ball position equal to ball position plus ball velocity times change in time, or delta t. Now, the real-world versus computational position graph is as shown. The computational position was slightly higher at the end than the real position, and we'll get into why that may be later. And for the computational velocity versus real-world velocity, we see that the computational velocity is constant throughout the entire experiment, while the real-world velocity that we observe from Tracker is very inconsistent, and it starts high and ends low. Now, possible errors for these discrepancies may be because of outside forces. Friction and air resistance affect the system and would cause the velocity to decrease over time and would make the final position less than the calculated position. Also, while tracking the position in Tracker, velocity was not constant because there were skipped frames in the video that caused these kind of spikes in the graph. This can be seen as we look at the first 3 frames are relatively consistent, and the third frame jumped quite a bit. This is because the frame rate wasn't exactly constant, so there were a little bit of stutters in the video. Now, a possible question for this experiment would be, what if the axes plus x and minus x were flipped? The numeric position and velocity values would change sign, meaning that positive values would become negative and the negative values would become positive. This would mean that the shape of the graph would remain the same, however, it would be flipped on the x-axis. The speed and the conclusion that the object is moving at a constant velocity would not change because the shape of the graph would stay the same despite the flipped sign of the values.